Here we are entering the Shevs' hometown of Trinidad and Tobago. Why does everyone look different here? These aren't polynomials. They're weird curves that intersect themselves. Where are the polynomials? Oh, I see one near the center. I'll go talk to it first and find out more about these other curves. I don't want to make a fool of myself. Hello there. You're the only polynomial I could see. It's my first time here. Can you please tell me who these other people are?
Oh, me? You think I'm a polynomial and the others aren't? Well, you've made a fool of yourself here, haven't you? Here, let me show you. You happen to see me from a particular angle. I'm like anybody else here, a sum of cosines, drawn on the surface of a half cylinder. Right. I'm cos of 4 theta by 3 minus cos of 3 theta by 4.
Whoa, you looked exactly like a polynomial earlier.
Huh. Okay, you should probably sit down. This might take a while.
Okay, cos of 4 theta by 3 minus cos of 3 theta by 4 was kind enough to explain everything to me. It's incredible. Just like a polynomial is a combination of 1, x, x squared, x cubed, and so on, these people are combinations of 1, cos theta, cos of 2 theta, cos of 3 theta, and so on. And each and every one of them looks exactly like a polynomial from some angle. The same way we plot the values of a polynomial as x goes between minus 1 and 1, we can plot the values of a sum of cosines as theta goes between 0 and pi. We plot this on this cylindrical surface. Here's what it looks like. We could continue plotting it till 2 pi, but it'll just be the mirror image of the part till pi, so there's no need to draw it. Now here's the fantastic part. Take the plane that is the open side of this half cylinder of radius 1. Let all the drawn points fall onto the plane. What you get on the plane is an actual polynomial curve. Alternately, you could just see the sum of cosines from in front of the plane. Once we remove depth distortions, we'll see the polynomial exactly. If you want to see the sum of cosines more clearly, you can also unroll the curved surface into a plane of length pi and draw the curve there. Let's take a simple curve, like cos of theta by 2. After drawing it, we curve the surface back and view it from the front. And it looks like a straight line. Let's see why this is. We'll take the help of the top view, which shows our progress on the curved surface more clearly. We plot starting from theta equal to 0, where its value is half. When viewed from in front, that clearly corresponds to x equal to 1 and y equal to half. When we try to plot it for some other values of theta, what are the x and y values that we see? The y value is simple. It would just be the same as the value of the function being plotted. So the y-coordinate in this case would be cos of theta by 2. For the x value, let's look at the top view. As you can see, the x value is the bottom side of the right-angled triangle with angle theta. So the x value would be cos of theta. That means we're just seeing the line y is equal to x by 2. Cos of theta by 2 was simple. But what about the function cos of 2 theta? At angle theta, we're plotting a point with the y-coordinate being cos of 2 theta. Again, angle theta corresponds to an x-coordinate of cos theta. So how can I write the y value, cos of 2 theta, in terms of the x value, cos of theta? We just have to recall the trigonometry we learned at school. Cos of 2 theta is actually just twice of cos squared theta minus 1. So on the plane, we're plotting y is equal to twice of x squared minus 1. Great. So what about functions like cos of 3 theta? You can try pausing this and working it out yourself. We know cos of 3 theta is cos of 2 theta times cos theta minus sine of 2 theta times sine theta. Knowing that sine of 2 theta is 2 sine theta cos theta, this becomes cos of 2 theta times cos theta minus 2 cos of theta times sine squared theta. Again, sine squared theta is equal to 1 minus cos squared theta, and we already know that cos 2 theta is 2 cos square theta minus 1. So now the whole expression is just in terms of cos theta, and it simplifies to 4 times cos cube theta minus thrice of cos theta. So this would give us the polynomial y equals to 4 times x cubed minus 3 times x. We can use induction to continue along these lines for any cos of n theta. If you're trying this proof by induction, it would be useful to also prove that sine of n theta is sine theta times a polynomial in cos theta. You can carry out these proofs just using the classic trigonometric identities shown here for cos of a plus b, sine of a plus b, and the one that says sine square theta is 1 minus cos square theta. And all these special polynomials, one for each cos of n theta, form the family of Shevs. This explains the behavior of the degree 5 Shev. It's just the polynomial you get by drawing cos of 5 theta on the curved surface and looking at it from the front. The properties we marveled at in the previous episode follow easily. Let's see it here by drawing cos of 5 theta on the plane above and tracking what value of x we get using the top view. Cos of 5 theta starts at 1 when theta is 0, which corresponds to an x value of 1. It goes to minus 1 when theta is pi by 5, which corresponds to an x value of cos of pi by 5. And it continues in this manner, while never going below minus 1 or above 1. So it has 5 arcs as theta goes from 0 to pi. We figured out the secret of the Shev. I hope I still have some things left to ask Shev when I meet him.
Hey fellows.
Hey Shev, we were just getting to know the people here. They explained to me how your movements are so precise. So what have you been doing here on your break?
Not much. I've just been practicing inside my own cylindrical arena instead of the plane arena for a change.
That's good. So I take it your plan is to first defeat all the polynomials that are projections of sums of cosines, and then to turn your focus to polynomials that aren't projections of sum of cosines?
You still haven't understood it completely. Every polynomial is a projection of some sum of cosine. Take the polynomial x cubed, for instance. I'll show you how to find out which sum of cosines will give you the polynomial x cubed. Let's start with the highest degree theta term, which shares x cubed since it's the only term. We can get that from cos of 3 theta by 4, because cos of 3 theta starts with a 4 cos cubed theta. Now we have x cubed minus 3x by 4. To make it x cubed, we have to add 3x by 4. What's important is that this has degrees smaller than 3. So we can add cos 2 thetas and cos thetas to handle it without affecting the degree 3 term at all. In this case, we add 3 cos of theta by 4, since that corresponds to 3x by 4. So cos of 3 theta by 4 plus thrice of cos theta by 4 will give you the polynomial x cubed. We could have done this with any polynomial, taking care of the highest degree term first, and then lower degree terms until all terms have been accounted for.
Wow, that's beautiful. So now you can make any polynomial a sum of cosines and then compete with it in your cylindrical arena. Is it easier to compete in your arena?
That's a hard question to answer. There are some peculiarities in the cylindrical arena. There are curves that I easily defeat in my arena, but that defeat me in the plane arena. Luckily, they're not polynomials, but it highlights some of the differences in the arenas.
How is that possible? Can you show me an example?
Sure. See this curve that barely increases at all? My maximum slope on the cylinder is 5, and its maximum slope is probably less than 1. I defeat it so easily. But look as we roll the plane into a half cylinder. At this end, there's no limit to how steep it becomes. Its slope keeps on increasing past any number you can think of.
Whoa. So even if you defeat all sums of cosines in your cylindrical arena, you still wouldn't have defeated all the polynomials in the actual plane?
As it turns out, defeating them in the cylindrical arena is actually enough. But to prove this requires a little bit of analysis. Let's do that now. Here's the top view again. Everything drawn on the cylindrical surface gets projected down to the plane. What we want to know is how slopes on the cylindrical surface translate to slopes on the plane. So here's a portion of the cylindrical surface. That portion gets projected to a certain portion of the plane. As we plot our function on the cylindrical portion, the function might have changed its value by some amount. And as we look at the resulting plot on the plane, the function will have changed its value by the exact same amount, since it's merely a projection that preserves the function value of each point. What changes is that the portion on the cylindrical surface has a long arc length, during which the function value made its changes. On the plane, the length of the portion is smaller. So in order to have the same change of function value, The plot on the plane must have steeper slopes. This is especially stark when we look at portions where theta is close to 0. With the same arc length as before, the resulting portion on the plane is tiny. The change of function value in the arc has to be done in a very short length on the plane. Now that we know what causes the change in slope, let's do a proper analysis of how the slope changes. You can pause and do it yourself if you want. Let's take an arbitrary value of theta and draw a really small arc at that angle. Now let's zoom in so that we can see it clearly. Since it's so small, it looks like a straight line. When this small arc is projected, the length of the projection would be what's shown here. We can compare the length of the arc and the projection by noticing that there are two sides of a right angle triangle. So the ratio is cos of this angle, but we don't know what angle it is. However, we also know that this angle here is theta. So our unknown angle must be 90 minus theta. And the ratio of the lengths of the projected portion and the arc is cos of 90 minus theta. Or in other words, sine of theta. That's the analysis of the slopes. The slope at a point on the plane is 1 by sine theta times the slope on the cylinder. So you see, I have a maximum slope of 5 in the cylindrical arena. It is still possible for a sum of cosines that I have defeated to have slope larger than 25 in their projection. But this can only happen when sine of theta is smaller than 1 by 5. Sine of theta is 0 when theta is 0 and is 1 when theta is pi by 2. If I split this interval into 5 equal parts, notice that sine of theta is smaller than 1 by 5 only in the part closest to theta equal to 0. That's because it has the steepest slopes there, and so it must increase past 1 by 5 in that interval. So if a sum of cosines I have defeated in the cylindrical arena has any chance of defeating me in the plane arena, it can only defeat me in these last intervals. But in the previous episode, we showed that no degree 5 polynomial can defeat me in my last arcs. Putting these together, there is no way for a sum of cosines I defeat in the cylindrical surface to defeat me in the plane.
So 2 questions. Firstly, all you have to do now is to show that the sum of cosines up to cos of 5 theta can't have a slope larger than 5 while staying between 1 and minus 1. What's your plan for showing this? And secondly, you seem to have a nice way of finding out slopes of the projections. We know from your polynomial representation that your slope reaches 25 at x equal to 1. How about for the other Shevs in the family? Finding out their polynomial representation and then differentiating them sounds complicated. Can you analyze their slopes more easily?
I'll start with the second question. We know that to find my slope at x equal to 1, you just find the slope of cos of 5 theta at theta equal to 0 and then divide it by sine theta. But that'll give you 0 by 0. So instead you have to find the limit as theta goes to 0. With a little bit of familiarity with differentiation, you'll see the result is 5 times minus sine of 5 theta divided by sine theta. Using L'Hopital's rule, for which I guess you'll provide the viewers a reference, you can differentiate this again and get minus 25 times cos of 5 theta divided by cos of theta. If theta equal to 0, this is just minus 25. So that's the answer. If you plot me on the cylinder near theta equal to 0 and project it on the plane, the plot will be moving down with a slope of minus 25 on the plane. And for my degree d siblings, the same calculation will get you d squared as the magnitude of their slope. Now for your first question. Yes, all I have to do is to show that any sum of cosines up to cos of 5 theta can't have a slope larger than 5, while staying between 1 and minus 1 on the cylinder. How will I go about doing that? I honestly don't know. The polynomial view had its process. You could shift it around and it would still be a polynomial. That doesn't happen for sums of cosines. And how many times can shifted sums of cosines intersect anyway? We knew that polynomials can intersect only 5 times. I feel like I lose my main tool when I go away from polynomial, but I'm done thinking about it for now. I'll just spend the rest of this holiday at home reliving my childhood instead of breaking my head. There's some mythological works of our people that I loved reading as a kid. Maybe I'll reread those. I remember one very mysterious one in particular. It was called The Legend of Half times x plus 1 by x.
Well, sounds like a great plan for a holiday. Thanks for the interview. I'll see you later.